Alright, welcome to Module 12, Part 1, okay, and so this is Chapter 9, and we're going to start with molecular geometry and bonding theories, okay, and the first part of this is really going to focus on molecular geometry, while Parts 2 and 3 are going to be more about the bonding theories. So we had previously been looking at Lewis structures to show the composition of molecules and their covalent bonds, okay, but the one thing that's missing is we're not talking about the shape of the overall shape of the molecule. So predicting the shape of a molecule depends on the electrons and the bonds in the molecule. Alright, so Lewis structures only account for the number and types of bonds in covalent compounds. Okay? But the shape of the molecule is actually determined by both bond angles and the bond length. So the shape really plays an important role in reactivity. Okay? And so if we look at the Lewis structure for CCl4, okay, which is shown here, we can see that we have a carbon in the central atom and 4 chlorine atoms surrounding that. Okay, but it really doesn't tell us anything about the shape. It's just a 2D drawing, right? But if we look at the overall shape, we notice that basically what happens is that we have 4 equivalent faces, okay? And so we have our carbon in the middle, shown here in gray, and then our 4 chlorine atoms shown in green, okay? There's a couple things to note here. One is that if we look at this picture, we can see that all 6 bond angles are spread evenly at 109.5 degrees. Okay, and all of these links between the carbon and the chloride is 1.78 angstroms. Okay, this is typical of what we call a tetrahedral shape. So when we talk about CCl4, okay, it's basically just a molecule with the general formula of A, B, N, okay, and basically that just means that we have one central atom connected to 2 or more atoms, okay, so A is our central atom and B is what's connected, and it could be 2 or more atoms. So then you could end up with something like AB2, right, you could have AB3, and so forth. So the number of shapes that are possible for molecules of A, B, N, right, really just depends on the value of N. So one important thing or concept for determining the shape of a molecule is noting the number of bonding and non-bonding electrons. Okay? Basically when we talk about bonding, it means that those electrons are involved in a bond. The non-bonding electron pairs are just the lone pair of electrons, which are not. Okay? Electrons in a molecule want to get out of each other's way. Okay, they want to be out of their way as much as possible to create the largest possible amount of space between them. Right? And so these electron pairs are termed electron domains. Okay, and it's very important that you can count the number of electron domains. The big take-home message that you need to get from here is that each non-bonding pair, single bond, or multiple bond is going to produce what we call a single electron domain. Okay, and that's around the central atom in a molecule. Okay, by being able to count these electron domains, you should be able to predict these different structures that you would have. So now we can turn to what's called the VSEPR model, the VSEPR model, Valence-Shell Electron-Pair Repulsion model. Okay, which basically says the best arrangement of a given number of electron domains is one that minimizes the repulsions among them. Okay, they want to spread out as much as possible. That's really what it comes down to, these different electron pairs. So we're going to talk about two things. We're going to talk about electron domain geometry, and we're going to talk about the molecular geometry. Okay, these are different. When we talk about electron domain geometry, we're talking about the arrangement of electron domains about the central atom of an ABN molecular ion. So this counts the free electron pairs, the non-bonding ones. We're also going to talk about molecular geometry, which is arrangement of only the atoms in a molecule or ion. Okay, if we can determine the number of electron domains, okay, which we can see over here, okay, then we can determine the electron domain geometry. Okay, so it's pretty straightforward. If you can count up the number of electron domains in a molecule, you should be able to predict the electron domain geometry. Back at this chart, and basically we can then determine that electron domain geometry. So now how do we determine the overall shape of the molecule? Well, there's 4 basic steps that you can follow. Okay, the first is to determine the Lewis structure, or draw the Lewis structure of the molecule. Then we can count the number of electron domains here, so which includes the number of lone pairs, which are non-bonding, and the number of single, double, and triple bonds. Okay. From there, we can then look at that chart table on the last slide and identify the electron pair geometry, which then, if we just count the molecules that are here instead of, or the atoms instead of the non-bonding electrons, then we can determine the molecular geometry as well using a similar table, which we'll see in a second. Alright, so a couple of important notes when talking about the effects of non-bonding pairs and when you have multiple bonds like double or triple bonds, and the effects these have on bond angles of a molecule. So non-bonding electron pairs, okay, are larger than bonding pairs, right? Thus their repulsions are greater, tending to decrease the bond angles in a molecule. So we can see that here, where basically we have this non-bonding electron pair, it's basically pushing everything else down, okay? Same thing here with water. Basically you have two non-bonding electron pairs which are basically pushing these hydrogens down and away. Pretty much similar with double and triple bonds are going to repel more than electrons of a single bond. Okay, so you can see here we have a double bond between the carbon and the oxygen, and it pushes the carbon chloride bonds down as well. Okay, so these are just basic things to kind of remember. Alright, well, some molecules, which we've talked about, have expanded valence shells, meaning that they may be surrounded by more than 4 electron pairs. Okay, means they have expanded octets. So for molecules with 5 electron domains, they have what's termed a trigonal bipyramidal electron geometry. Okay, of those 5 electrons, you can basically see that we have 3 electrons, which 3 electron pairs on the equator. Right, so you can kind of see this blue triangle shown here. Okay, that's our equator, and 3 of those electron domains are shown there. 2 of them, though, 2 electron pairs are actually above and below this equator, and so we call these 2 axial electron pairs. Okay. For molecules with 6 electron domains, they can have what's termed an octahedral structure, where 4 of those electron pairs are equatorial and 2 are axial. Okay. So here's an overall table of all the geometries, and you can basically see that if you look, you can look at the number of electron domains. Once you identify that, you say, okay, there's 5. Well, the electron domain geometry has to be trigonal bipyramidal. Then we can look to identify the molecular geometry by looking at the number of bonding domains and non-bonding domains in that compound. So if there's 4 bonding and 1 non-bonding domain, then we have what's termed seesaw. Okay, so this is really how you'll go about this. Same thing if you just looked at basically here, where you have 2 electron domains, you would know the electron domain geometry is linear, which means that you have 2 bonding, no non-bonding, and so your molecular geometry is also linear. Okay, so it's critical that you can identify the number of electron domains. Alright, you could encounter these larger molecules, or molecules with more than one central atom, and we can basically just say, okay, well, in order to identify the geometries, basically just look at one central atom at a time. Okay, and so here we just basically look at this carbon, then we can look at this carbon, and then we can look at this oxygen. Okay, and so you can see that here, how it's just basically broken up, and each one has its own geometry. Alright, so the last thing we're going to talk about is bond polarity. Alright, and if you remember, bond polarity is just a measure of how equally the electrons in a bond are shared between the 2 atoms of the bond. So the greater the difference in electronegativity, greater the polarity. Okay, we've been looking at dipole moments, right? So we talked about the dipole moments of just diatomic molecules, atoms made of just 2, or molecules made of just 2 atoms. Okay. But now we're going to look at molecules with more than 2. Okay, so if you remember, we talked about the bond dipole, which was just the dipole moment due only to the 2 atoms in that bond. Right? But if we look at something like CO2, okay, shown here, there's 2 bond dipoles. One between this carbon and oxygen, and the other between this carbon and oxygen. Okay, and so basically we can add the individual bond dipoles and determine the overall dipole moment for the molecule. Now, one thing to note is that bond dipoles and dipole moments are both vector quantities. It means they have both a magnitude and a direction, right? So they're pulling one way, and there's a magnitude of how hard that's pulling as well. Okay. And so to determine the overall dipole moment, you need to account for both of those. Okay. If we look at water, basically you can see that based on the molecular geometry, we have this bent molecular geometry, but the oxygen here is pulling the overall direction one way, and this other oxygen hydrogen is pulling the other direction, and so the overall dipole moment is actually just up. Okay, and the length of this arrow kind of tells you how strong it is. And so it can tell you if that's a polar or non-polar molecule. So when we talk about polar, it means that basically it's not all equal, whereas non-polar means it is. Alright, so CCl4, as we looked at from the beginning, basically we have a carbon, and each of these chlorides are spaced evenly, pulling same magnitude, opposite directions of one another, and so basically nothing's happening here. Okay, you can think about which way you would think it would move. And so CCl4 is non-polar. Same with BF3, whereas HCl, right, this is a basic diatomic molecule where you basically have a chloride which is a lot more electronegative. It's going to pull that electron away from the hydrogen, and so it's polar. Okay, and you can see a couple other of these where you have NH3 or CH3Cl. So that concludes part 1, and good luck with chapter 9. Make sure you practice drawing those Lewis structures, identifying the electron domain geometry and the molecular geometry.